Alright, so this round we're taking a look at Newton's second law of motion. So go ahead and write this one down already. It's right here, right off the bat. Actually, I take that back. Sorry, we're not going to define it just yet. It's going to come up in a minute here, the better definition of it. But Newton's second law of motion is related very closely to it, right? I mentioned that before, that Newton's first law talks about the cause of a change in motion being a force. So force is causing a change in motion. Change in motion is the same thing as change in velocity. Change in velocity is the same thing as acceleration. So a force causes acceleration. So just a refresher of what acceleration is. A change in velocity is that there is an acceleration. So Newton's first law says that a net external force causes acceleration. So we also need to remember what an external force is, right? An external force acts from outside the system of interest. That means it's coming from outside of it, not something within. So in the second here, we're going to look at a picture with a kid in a wagon. The child in the wagon is putting a force on parts of the wagon, but those are internal forces. They're not affecting his motion. What's happening outside of that, he's being pushed in the wagon. Those forces are external, and those are what are affecting the motion of the wagon. So another thing I do want to have you jot down here is that you must define the boundaries of the system before you can determine which forces are external. So that means we have to pick the system of interest in order to figure out what forces are actually acting upon that system. Sometimes there's more than one option, and drawing all that stuff out might help to see what you really need to put your focus on in order to find what the question in play is asking you to find. So again, here we do talk about we talked about weight being a force before. We talked about friction a little bit. There's also something called the normal force that we're going to look. We're going to look at all of these other forces down the line, and we'll use them a little bit at a time. But that's what you're about to see in this picture here. So here we have a couple of situations. The kid in the wagon's there. He has a weight that's going down. He has a normal force that's counteracting that weight. So those two counteract each other and basically make it so that we don't need to worry about them for this particular situation. The main forces acting upon this body or this system are the forces of the people pushing the wagon and the force of friction against that push. So in the first situation, there's two little girls pushing the boy in the wagon, and each of their forces combine together to counteract that frictional force and push him along and accelerate him along to the right. You can see that in the free body diagram. We would ignore the normal force and weight because they balance each other out, and then add up the two frictions pointing to the right, subtract the frictions, the two forces going to the right, subtract the friction that's moving to the left, and that will give us our net force acting on that system. And the same thing applies for the second image here. We have now an adult pushing the child in the wagon. Again, there are internal forces happening here, right? He's sitting on the wagon. That could really affect it, but probably not. That probably is just adding more to the frictional force than anything. He could be gripping that handle and making it steer a little bit differently. There are other forces that could be affecting that are internal, but they're highly unlikely to really affect anything. But for the second version with the adult, she's pushing with a larger force than the two individual girls together were pushing with. So you can see the arrow is much longer for the adult than the two children. And again, we would just take that force, subtract the frictional force away, and voila, we have our net force. So, how choice of the system of interest affects the forces that need to be considered? Well, if we don't pick the right system of interest, we might be including forces that are not really pushing the system along, or we might be excluding forces that are actually going to cause the system to move the way it's moving. So we have to be careful and find that right balance that is the actual system of interest what we're looking at. Later on, when we look at Newton's third law, we'll see that there are options sometimes, and we might have to go big picture first, and then go down to the smaller. I guess I call them subsystems whenever it's a system that's within another system, or we might have to go subsystem first, then broad overall picture. Just it varies depending on what is happening in that situation. So we've already talked about external forces, and again, friction is going to cause some problems later on for us down the line, but this is an important thing here. Now they do use W for weight, not a fan of that, because we will use the other things with W later on that like work, and then we'll use a lowercase omega, which looks like a W as well when we get to angular velocity. So we try not to use W for weight. We usually just say it's F with a little g as a subscript, so you know it's the force due to gravity. Normal force is also not usually capital N. Sometimes it is, but a lot of times we'll label that as Fn, which is the normal force then. F net is the net force. I do use a small, like almost cursive like F for friction, so that way it distinguishes itself as well. They just use a lowercase f, but here we go. We will define friction here. Now we'll define it again later on too, but it is the force that opposes the motion past objects that are touching. Now I don't really like the wording too well here, but it is okay. So as a force that opposes the motion of objects past each other that are touching, or like maybe just rearrange it a little bit. It works much better to me, but that's all right. And then, of course, we do also want to sketch this little thing here. You may not be familiar with that symbol in the middle, but that symbol just means is proportional to. So the acceleration is proportional to the net force, is what that's saying. So there is the explanation of that symbol there, again, what that means. But really what it means is that when we set up an equation, the force will be on one side of the equation, acceleration will be on the other side of the equation. One of them or both of them may be multiplied by some other number, but they are proportional to each other because they are equal, but with one maybe being a scaled up or scaled down version of the other. Now, keep in mind this also means that as one of them is going to go up, the other one is also going to go up. So that's kind of the nice thing about proportionality, is that if the acceleration increases, the force is going to increase as well, as long as other things stay the same. There is that little caveat that we have to keep something else the same in order for that to happen. Which usually that just means the mass. And so here's where mass plays in. So acceleration is proportional to the inverse of the mass. Or you can say that that is the acceleration is exactly inversely proportional to the mass. Just as it is exactly linear proportional to the net external force. So this means that if they're inversely proportional, either they'll be set up like this, where it's equal, so acceleration is equal to 1 over the mass, or if you have that situation, I don't have to write this down, but if I have that, this is not true. But if I have this, then I can multiply by m on both sides. And mass times acceleration is equal to 1. So they might look like this, or they might look like how it is right now with an equal sign 1 over. But for our sake, it's going to be mass times acceleration. And not only is it mass times acceleration, if I change that F or 1 to an F, that is Newton's second law. And you'll see that in a second. So just like the proportionality of force and acceleration, they increase together, they decrease together. Mass and acceleration do the opposite. So if the mass acceleration goes up, so if we want to keep the force the same and the acceleration increases, then the mass has to decrease, and that's what this is showing here. So, or vice versa, if the mass increases, so going from a small basketball to a large car, but applying the same amount of force, then our acceleration is going to go from some large acceleration to a very tiny acceleration, because the car is so much more massive than a basketball. And if we're applying the same amount of force, it's not going to accelerate as fast as the basketball will. That just doesn't make any sense for that to happen that way. So that's what we're really looking out for here. So a system can have non-zero velocity while the net external force on it is 0. So this one I proposed in class, and it was a stumper for some people. It took some finagling to get the right answer out. So it says describe such a situation, but really there's one situation that this is true. If our system has non-zero velocity, it is moving. It has a velocity that is a quantity, is a number other than 0. But it has net external force that's 0, which means, remember, net external force means that there's a change in motion and acceleration. But if it's 0, then there is no acceleration. And if there's no acceleration, but there is a velocity, then our system is moving with constant velocity. And that is the only way this is possible. So it has been found that the acceleration of an object depends only on the net external force and mass of the object. Combining the two proportionalities that we just saw earlier finally gives us Newton's second law of motion. And I'm going to skip this problem to get there. I don't know why they threw in another problem to help guide us on it, but here it is. Fine. Newton's second law of motion. So you can see they took these two, right? So here's the proportionality part. And then here's the inversely proportional part. You combine those together and you get Newton's second law of motion. And then we rewrite that as force net equals mass times acceleration. Now that's true for every system. So if we are given a system that we are dealing with multiple forces on, we know that the net force, no matter what, is going to be mass times acceleration. The net force might be some addition, subtraction, whatever, of a few different forces occurring on the system overall, but it is also always mass times acceleration. So we can then use that to get two different quantities for the net force that are equal to each other. So we can then set those two equations equal to each other and solve for what we are looking for. That is what we need to be doing for the problems for this example here. So do write that this is Newton's second law of motion. You don't have to write the proportionality part, but at the very least, that Newton's second law of motion is F net equal ma. So we now have Newton's first law, that's our law of inertia, and Newton's second law, which is F equals ma. So this law is the cause and effect relationship among three quantities that's not simply based on their definitions. The validity of it is completely based on experimental verification. And we already did that a little bit with the carts, where we pushed and pulled the cart for 10 centimeters and looked at the force that we caused and how the mass and acceleration. We really actually, if you look at the answers to the questions on it, and we did that on the warm-up for today as well. I didn't go over that with you here, but when we graphed the data from that cart, we had the y-axis be the force, we had the x-axis, force, the y-axis was force, x-axis was acceleration. Slope of that line was the mass. So if you think about it in terms of F equals ma, or y equal mx plus b, ignoring the y-intercept, saying that's 0, then your m is your slope. It's also your mass. Your x's were the acceleration, right? So a, so m times a, and our y-axis was our force. So y is F. F equals ma. And there we go. So here's another scenario. A rock is thrown straight up. What is the net external force acting on the rock when it is at the top of its trajectory? Now, the nice thing about this one is that it does not matter what part of its trajectory it was in. It's always the weight. If any object is in free fall, the only force acting on it, ignoring air resistance, is the weight of that object. So we already talked about unit of force, but here we are with what a Newton really is broken down. It's a kilogram meter per second squared. That is mass times acceleration, right? And we also are given this conversion between newtons and pounds. So 1 newton is 0.225 pounds. Now, typically when people outside of the U.S. go to the doctor, they're not going to tell them their weight in newtons. They're going to give them their quote-unquote, if you could see me, I'd be doing air quotes, their weight in kilograms. But that's not true. They're giving them their mass, not their weight. And somebody asked in class, well, how does a scale know that how much matter is on top of it? Well, it actually uses this situation here, knowing that we're on Earth, so your gravity is 9.81. So if it's a digital scale, it's going to take that out of that, whatever the force is in newtons. It's going to divide by that and give out the mass. If it's a analog scale, then it already has that set into the printing of the scale to do that. And so that also kind of leads you into, well, if you Google how to convert from kilograms to pounds, you can do that because of Newton's second law. Because I know that a Newton is a kilogram meter per second squared, right? So if I'm looking for how many pounds per Newton, right? So we can use this conversion here, 0.225. Well, this is the same thing as 0.225 pounds over kilogram meters per second squared, right? Because they're the same thing. So if I multiply this, by 9.8 meters per second squared. That's going to cancel out by meters per second squared on the top and bottom. Now I'm just left with pounds over kilograms. So pounds per kilogram. Just to show you where they get this conversion from, you don't have to write this down at all, but 0.225 times 9.81, 2.207 pounds. So 2.207 pounds equals 1 kilogram. So that's where they get that conversion from. I wouldn't write this down because, again, it's not a conversion that is really an actual true conversion. It's a conversion that is using Newton's second law as a formula and a calculation to get from force to mass in two different systems. So which statement is correct? Net force causes motion, or net force causes change in motion? Well, we have already said that force causes change in motion. So net force causes a change in motion. Not that it causes motion. It might be the cause of something coming from rest into a motion, which is true, but it's still causing a change in motion. Not that it's just going from 0 to whatever quantity. It's still a change in motion, not necessarily just adding motion. So I mentioned this earlier, weight, gravitational force, they're the same thing. Weight is the force due to gravity. And again, they like to use this W all over the place. I don't like that, but there we go. So weight is just mass times gravity. Instead of mass times acceleration, our gravity is the acceleration in that case. So here's the equation for weight. So weight is the gravitational force on a mass. I'm going to go and highlight extra here because I'm going to write down how we're going to explain or abbreviate for weight, not using W, but there we go. And they do go ahead and figure out the weight of a 1 kilogram object is 9.8 or 9.81, depending on where you round the acceleration due to gravity. And here we have free fall. When an object's net external force on an object is its weight, we say it is in free fall. So again, that means that anything that is in the air that is just falling, then it is in free fall, or even if it's thrown up, it's still in free fall. The only force acting on it is gravity. And again, here they do mention how that changes depending on where you are. And again, we mentioned this already. I'm not going to continue to rehash it too much because we will bring it back in here. We talked about it with inertia as well. Weight and mass are not the same thing, even though they may be used interchangeably. People might say weight is in kilograms, and it's not, no matter how much they want to try to say it is. And again, one more time, rehashing that. Weight and mass are not the same thing. And same for this. The take-home experiment, if you want to go for it, have at it. If you've got it in a bathroom scale at home, then be my guest. Try something out. So here we have a problem now. We have this mower that's being pushed with 51 newtons parallel to the ground. The mass of the mower is 24 kilograms. We want to know what its acceleration is. And I am going to go ahead and work this problem out. Granted, if you do open the nearby that's on there, you could just go ahead and scroll through as well. But we know the friction force is 51 newtons on the ground. So first of all, we have our picture drawn, but let's draw a free body diagram. So we have this net force acting. We have the frictional force. Actually, what are we trying to find again? The acceleration. I don't need this. Don't need a free body diagram for this. Sorry. Just thinking about future problems. Alright. Sorry about that. So, net force is given to us 51 newtons, and that's already having the frictional force taken out of it. So mass is 24 kilograms. We want to know acceleration. F equals ma. So that's 51 is equal to 24 times a, dividing by 24 on both sides. Cancels the 24 on the left or the right, whatever it is. Unfortunately, I can't pull up a calculator to show you this on here when I do screenshots, so just gonna have to trust me. That 51 divided by 24 is 2.125. And meters per second squared. As long as everything's in our standard units, like newtons and kilograms, then our unit for acceleration is meters per second squared. And so there's their work for it as well. Same thing we got. So we're good there. So now, in addition to that problem before, same situation, same mower. Still has a mass of 24 kilograms. Net external force is 51 newtons still. The force of friction opposing it is 24. We want to know a couple things here. So, first of all, what force is the person exerting on the mower? So we'll call that part A. And then part B is the last part here. Alright, so for part A, we're looking for, now we want that free body diagram. So he's applying a force on the mower. We'll call that force FP for the person. And there's the frictional force going the other way. But we also know net force already, we know is 51 newtons. We know the frictional force is 24 newtons. We don't know FP. So remember, net force is mass times acceleration. We already dealt with that. We don't need to worry about that. We know the net force already. So we don't need to set up two equations like we normally would. We do have normal force and weight, though, counteracting each other in this free body diagram. Always need to draw those. But our net force is equal to mass times acceleration, sure. We already know what net force is, so we don't have to do that part of it. We also know that it's equal to the force of the person minus the frictional force, which means it's just 51 is equal to the force of the person minus 24. So you could add 24 to both sides. So that's going to be 75 newtons that he's applying to the mower. Now, second part of this. Suppose the mower is moving at 1.5 meters per second when the force is removed. So for part B, new free body diagram. So now it's just got this one force acting, the frictional force. We want to figure out how far it's going to go before stopping. So we need to figure out how far it went, right? That's what it's asking us, distance-wise, displacement. So we're going to go back to our kinematics here. And we need to write out what we have, right? So we have our initial velocity is 1.5 meters per second squared. We know our final velocity should be 0 meters, not meters per second squared, meters per second. We're looking for displacement. We need to figure out one other thing, though. We need to figure out the acceleration, because we don't know that, but we do know that frictional force is 24 newtons. And that's also now the net force acting on it. So our acceleration has changed from what it was on the previous problem. Sorry about that. So our frictional force is equal to mass times acceleration. So that's 24 equal to 24 times A, because our mass is also 24 kilograms. The mower didn't change, still the same mower. Dividing by 24 on both sides, it's going to give us our acceleration that we need to do the rest of the problem. This is 1 meter per second squared. So now I'm going to zoom out a little bit here. We need to figure out what kinematic now we need to use that has initial velocity, final velocity, displacement, and acceleration. And that is the one that's 2a delta x equal to final velocity squared minus initial velocity squared. We can eliminate our final velocity squared part, because that's 0. Now we do have to keep in mind that this acceleration, the frictional force is really a negative 24. It's moving to the left. It's moving to the right, but the frictional force is to the left. So this is actually a negative 1 meter per second squared for our acceleration. It's going to make a difference here, because now that we've eliminated that final velocity, we'd have a negative at the end. And we don't want that for displacement here, because it is moving forward. So it's a negative 1 here, delta x equal to negative times 1.5 squared. So that's negative 2 delta x equal to negative 1.5 squared is 2.25. We're going to divide by negative 2 on both sides. That will cancel out our negatives, which is what we needed to have happen. And our displacement comes out to be 1.125 meters. That's how far that mower is going to continue after he lets go. Sorry, I didn't mean for that loud noise there. Alright, so here we have a different situation. We have a rocket that's gliding, and there's some known things here. The acceleration is 49, the mass is 2,100 kilograms, and the force of friction is 650 newtons. So here is our picture with free body diagram that I'm going to go ahead and screenshot and do the work on here. So here we have our picture. Free body diagram is helping us out a lot here. Again, just like as before, the normal force and weight are going to cancel each other out. So our net force, again, as I mentioned before, net force is always mass times acceleration. In this particular case, the net force is equal to 4 times the thrust. It's on there, 4 times to the right, minus the thing going to the left, our frictional force. Now we're looking for what thrust is. So we know our mass, that's 2,100 kilograms. We know our acceleration is 49 meters per second squared, and we know our frictional force is 650 newtons. So we can set, because again, no matter what, if we have one system we're looking at, our net force is always going to be the same thing. So net force is mass times acceleration, and net force is equal to 4t minus friction. They're equal. So 4t minus friction is equal to mass times acceleration. You can write it the other way around too. I just like to keep the variable we're looking for on the left as much as I can. So plugging everything in, 4t minus 650 equal to 2100 times 49. So first things first on the right, that 2100 times 49 is 102,900. We're going to add 650 to both sides. So that is 103,550. And now I need to divide both sides by 4. And that's going to be 25,887.5 newtons. It's a lot of thrust, and it's 4 times that in here. So hopefully that's a good lead-in to what we're going to see for Newton's third law. Because we're going to have a few problems where we have to pick the system the right way and do this same type of problem where we're going to look at the net force in both situations. So looking at their work, they do it the same way. Net force as MA, or 4t minus friction. Set those equal to each other. They did some manipulating first before the calculations, but they also rounded and used scientific notation. Not the biggest fan of doing that in this case, but that's okay.